Now we're really ready to build a circuit that can add two numbers, and this will be representative of the kind of calculations that we want to do with our computing devices. So let's make an adder. So we're going to do an 8-bit adder, and so what we want to do is say that we have two binary integers, x and y, in this case 8 bits, and we want to compute the value of their sum. So here's an example, and we've done binary addition in many cases before. So this is 0, 0, 0, 1, 0, 1, 1, 1. So that's 16 plus 4 plus 2 plus 1 is 23. And then the other one is 32 plus 16, 49. So 23 plus 49 is 72. That's what we're trying to compute here. So what we'll do is, in our adder circuit, we'll take inputs, and we're going to need those inputs all the way through the circle. So at the top is the first binary number, 0, 0, 0, 1, 0, 1, 1, 1, which is 23. And then the next input is the bottom binary number, 0, 0, 1, 1, 0, 0, 0, 1. That's 49. So that's our inputs to the circuit, and again, usually inputs come at top or left. And then the outputs will come out on the bottom, in this case 0, 1, 0, 0, 1, 0, 0, 0, which is 72. So we want to build a circuit that has this behavior. We're going to ignore overflow. There's actually, if the number gets too big, then it would carry out a 1. We could catch that, but we're going to ignore it for now. So in general, this is with all the inputs labeled symbolically. We're going to have 8-bit numbers, x7 down to x0, y7 down to y0. Our inputs and our outputs are z7 down to z0. And then we're computing the sum symbolically shown at the bottom left, and we're going to ignore the carry out. So we just learned how to implement a circuit that can implement any binary function, and this is a binary function. So one thing that we might consider doing is build a truth table for each output bit. For 8-bit adder, well, we've got 16 inputs, and then we've got, well, if you count the carry, 9 output bits. But there's way too many rows. There's 2 to the 16th different possibilities of the inputs, 65,000 rows. And if that doesn't seem bad, say in a real computer you might want a 64 or 128-bit adder. If you were to use this method for that kind of application, you'd have 2 to the 256 rows. And we've already calculated that's bigger than the number of electrons in the universe. So what Shannon and Boole tell us is that it's possible to build such a circuit, but not necessarily the most efficient way. So we're going to look at a much more efficient way to build an adder circuit. And it's a very simple idea. It corresponds to what we do when we're trying to add. We're going to do 1 bit at a time. So like, what do we need to do to implement the carry bit when we're adding the first 2 bits? Well, the carry bit, if x, y, and the carry in are 0, then it's going to be 0. Or if it's 0, 0, 1, it's going to be 0. It's only going to be 1 if we have 2 1s or 3 1s. Does that sound familiar? Well, it is, and we'll see in a second. And similarly, the sum bit. It's going to be 1 if exactly one of them are 1, or if all 3 are 1, and then there's a carry out. If all 3 are 1, the sum is 1, and there's a carry out. So those are the functions that we need to compute, but those are the functions that we know. The carry bit is the majority function. The sum bit is the odd parity function. So we already have the circuits that we need to compute the 1 bit at a time, compute the carry and the sum. And all we need to do is connect those circuits together to get our job done. And that's what this does. So at the top is a majority function for each bit. At the bottom is an odd parity function, or the sum for each bit. Both of those functions take 3 inputs. The 3 inputs are our input bits, x and y, and a carry bit. and the carry bit comes from the circuit to the right. Starting with a 0 over at the left, then the output of the majority function, over at the right, the output of the majority function on the rightmost is routed through the middle and up over to be a carry input into the secondmost from the right, and so forth. So the carries are routed out and up to the next one to its left. And these 1-bit adders are chained together with the carry, which ripples through. Now this design is called a carry ripple adder. And obviously the same design extends to any number of bits. And that's our adder circuit. So here's our adder circuit magnified, and we can take the covers off to reveal the circuits inside that we've already talked about. On the top is the majority circuit for each bit, and the bottom is odd parity for each bit. And if you examine this closely, you can see the sums being computed and the carries coming out exactly as in our example. An 8-bit circuit for a circuit for adding 2 8-bit numbers where we can see the function of every switch in the circuit. This example illustrates again the lessons of software design that really apply to hardware. The interface gives the behavior of the circuit, the implementation gives the details of how to build it, and we just exploit our understanding of the behavior at each level. In order to implement the add, we needed to implement a Boolean function. We knew how to implement those Boolean functions. We start with a controlled switch. We build gates. From the gates, we can implement Boolean functions, and after a while, we have an adder. Next, we'll look at how to incorporate the adder into an arithmetic logic unit, and eventually to an entire central processing unit in the next lecture. This approach vastly simplifies, it not just vastly simplifies, it makes possible the design of complex computer systems. And not only that, it enables the use of new technology at any layer. If we want to work hard on developing a better adder, we can plug that in at any level. And in fact, computers today use a more efficient adder. This one takes time proportional to the number of bits to ripple the carries through. And it's possible to cut down on that time by a log factor. So next we'll look at the arithmetic logic unit.